Okay folks, this is the third and final video on the chain rule. I'd really recommend you watch the first two first, obviously. We're going to have a look at some shortcuts this time. So over on the left hand side there, you've got all of the things we looked at in the last couple of videos. We're now going to try and introduce three shortcuts. And the first one of those is for exponentials, by which I specifically mean e to the x. We're not going to talk about those general a to the x's. Shortcut is this: if we have y equals e to the fx, and fx is just shorthand for some sort of function of x, so it could be anything in there, then the differential of that is f dash of x. So f dash means the dy dx essentially of that function. I think we've used that notation before, but just in case, times e to the fx. Now it would probably be worth proving this, just because I feel like it's not good for me to just state something. Let's use the chain rule to do it. If we were going to say that we had y equals e to the fx, then we could say, well, we can break that down into y equals e to the u and u equals fx. Now we then need to differentiate each of them according to the chain rule. So first we'll do dy du, which is e to the u, and then we'll do du by dx. Now, as I said up here, f dash is the shorthand for the differential of. So du by dx is just f dash of x. Chain rule, we multiply these two things together. So that would tell us our dy by dx is equal to e to the u times f dash x. And we know u is f to the x. So we know it's e to the fx times f dash of x. And if we rearrange the order of our multiplication, we get that idea. Okay, so let's actually try and apply this here. And we're going to do these a lot quicker than the chain rules we looked at last time. This is going to be like a rapid fire way of doing it. So what would I do here? I'd say I've got y equals e to the 5x, okay? So I'd say, well, okay, so my fx is 5x. If I differentiate that, I get 5, so let's put that in. I've got 5e to the 5x. And I'm sure that's a shortcut some of you noticed before. It's not quite the case that we just multiply by the number, but it is definitely the case that we multiply by the differential of whatever that's there. Okay, let's do another one. In this case, I've got fx is x to the 4. Differential of that is 4x cubed. So I've got 4x cubed e to the x to the 4. Now, when you get good at this, you don't need to obviously write this out. You can go straight from there to there and just think, well, I'll just write my e to the x to the 4 and differentiate it and stick it at the front. Last one, fx is cos x. Differential of that is minus sine x. So we've got minus sine x e to the cos x. Easy as some beans. Second of our three shortcuts is probably the cleverest, and that's if we've got the natural logarithm of fx, ln, then the differential of that is f dash x over fx. Now again, let's do a little bit of a quick proof here. We're saying y equals ln u, where u equals f of x. If we differentiate this, pen's really not behaving today, dy by du is 1 over u, and du by dx is f dash x. As mentioned before, that's what differentiation is. So our dy by dx is equal to dy by du times du by dx, which is going to be 1 over u times f dash x, which is 1 over fx times f dash x. So that gives us overall f dash x over fx. Great, there's a proof. How do we actually use this though? Well, it just means that whenever we want to differentiate something which is a natural logarithm, we write ourselves a fraction. So I can sort of set these up. I know I'm going to have an answer as a fraction, and I might need to simplify it in the end, but that's fine. And the fx, the thing that we've got the log of, that goes on the bottom of the fraction. So 5x goes here, and x to the 4 goes here, and cos x goes here. And then on the top of the fraction goes the differentiation of that. So the differentiation of 5x is 5. The differentiation of x to the power of 4 is 4x cubed. Differentiation of cos x is minus sine x. And that's basically all there is to it. Now in these cases I would probably tidy these up a little bit. They can certainly be simplified. The 5's cancel on that one, so it's 1 over x, which is cool. On the next one, the x cubed and the x4 will cancel out. So we'll have 4 over x left over. And on the very last one, well, sine over cos is tan. So I could also write this as minus tan x. But you've got the mark at this stage, unless they specifically say fully simplify. So our third and final shortcut is one that we can use with brackets, and it is that if we have a function to the power of n, then we stick that power of n outside of the bracket, that we have the differential of that function next, and then we have the original function with a reduced power, or in algebra, exactly what it says there. Again, I'd like to prove this using the chain rule just to show it's all legitimate. We are saying in this case that we've got y equals u to the power of n, and our u is equal to f of x. If we differentiate y, we get times by the power, so n decrease the power u to the n minus 1. And if we differentiate this, we still just get f dash of x. Putting that all together, multiplying those together for our dy dx, would give us n from the dy du, f dash x from the du dx, u to the n minus 1, and then we can obviously just swap in the fact that u is equal to fx. There we go. So it does work. Let's actually see how it works in practice though. So in this case, I've got y equals 5x plus 3 to the power of 7. So in this case, I'm saying my fx is 5x plus 3. I know the differential of that is 5, so I'm good to go now. So it's going to be n times f dash x times 5, and then times the bracket, so times the 5x plus 3 with the power decreased by 1. Tidy it up, 7 times 5 is 35, don't need our times signs in there, 35, lots of 5x plus 3 to the 6. Second one, in this case, our fx, the thing that's inside the bracket, is ln x minus x. So we need to differentiate that, and if we do, we get 1 over x minus 1, and then we can go straight into the little shortcut thing, so it's going to be n, which is 3, f dash x, which is 1 over x minus 1, and then fx, which is ln x minus x to the power of n minus 1, so to the power of 2. I don't think that tidies up any nicer if we simplify it, so we'll leave it like that. Third one, we've got a function this time of cos x minus sin x inside the bracket. So if we differentiate that, we're going to get minus sin x minus cos x, refer to your circle of trig. So if we then want to use the shortcut, it's going to be n, so that's 5, f dash x, so that's minus sin x minus cos x, and then fx to the n minus 1, so cos x minus sin x to the power of 4. Now, if it were me, I might want to take this minus sign out to the front, but otherwise that doesn't really simplify much down. So yeah, it's a little good bracket shortcut, that. Now, once you've actually internalized those shortcuts, it makes these sort of questions very, very rapid fire. So in this question, I'm just going to do these 9 in rapid succession. You might want to try and have a go first and see how fast you can do them. So first, we're just going to circle all of our fx's, because these are the things we're going to need to differentiate. These are the things we're going to need to find the f dash x's for. So I can say in this case, well, my f dash x is 2. In fact, let's just make an extra column for these. F dash x. So we've got 2, 3, minus 1, 2 again, 5, 2, 4, minus 2, and 2x. Okay. And I'm going to use all those to quickly come up with my actual shortcuts. So let's do the exponentials first. It's just f dash at the front, so this is 2e to the 2x. And this is minus e to the minus x. And this is 2e to the 2x plus 1. And there we go. What about the logarithms? Well, logarithms, we said they are all fractions, so we can put the fractions in. On the bottom of the fraction goes the function, 3x, 5x minus 1, 1 minus 2x. On the top of the fraction goes the differential of the function. And in some cases, well, just this case here, you'd be able to simplify that. And lastly, we've got our brackets. So it's going to be n f dashed. So this one's going to be 3 times 2, so 6 fx to the n minus 1. Then do that again. N f dash, 4 times 7 to 28, fx to the n minus 1. N times f dash, that's 10x this time, 5 times 2x, fx to the n minus 1. Super easy, super simple, and those would have taken a long time in the previous two. But we've got to know where they came from.